10 years ago, we decided to build the biggest scientific experiment ever built, 16 miles in circumference underneath Geneva.
In September 2008, after years of waiting, the Large Hadron Collider, LHC, the most advanced high-energy particle collider on Earth, finally kicked into gear. Constructed by the European Organisation for Nuclear Research, building it was no small feat. Since then, the LHC has deepened our understanding of the universe significantly. But recently, something unexpected shook the scientific community. When CERN scientists cranked the LHC up to its highest energy level, they stumbled upon a puzzling result. Now, scientists are scrambling to make sense of this surprising development. What exactly happened, and what does it mean for the present and future of science? Join us as we delve into the mystery. Imagine a colossal machine stretching across 2 countries and burrowing deep beneath the Earth's surface. That's the Large Hadron Collider, LHC for you, a marvel crafted by CERN. But this isn't just any machine, it's the biggest and most powerful particle collider ever built. And the story behind it is just as captivating as its purpose. CERN, known formally as the European Organisation for Nuclear Research, stands as a symbol of global unity and boundless scientific curiosity. Its story goes back to the aftermath of World War II. In the wake of the war's devastation, there was a shared belief among scientists and leaders that collaboration held the key to rebuilding Europe's scientific strength. It was in this spirit that, in 1950, the renowned physicist Louis de Broglie suggested the idea of creating a joint European laboratory to ignite scientific creativity and foster peaceful relationships. Not long after, in 1952, 11 nations joined forces to sign the CERN Convention, giving birth to the organization. Fast forward to 1957, and CERN was officially inaugurated on the border between Switzerland and France. At its core, CERN's mission was to delve into the mysteries of atomic nuclei and their fundamental particles. To accomplish this ambitious goal, scientists needed powerful tools, particle accelerators. These colossal machines propel particles to incredible speeds, allowing scientists to collide them and unlock secrets about the universe's fundamental building blocks. Fast forward to the 1980s, and the concept of the Large Hadron Collider, LHC, began to materialize. With scientists' aspirations reaching new heights, there arose a demand for a more potent tool to delve deeper into the mysteries of matter. The LHC emerged as the brainchild of this ambition, envisioned as the world's largest and most robust particle accelerator. It boasted a 27 kilometers loop of superconducting magnets and detectors. The construction of the LHC kicked off in 1998, marking a remarkable feat of engineering. Nestled 100 meters beneath the Earth's surface, this colossal structure required the collaborative efforts of thousands of scientists and engineers from across the globe. It took a decade of relentless work, and finally, in 2008, the LHC was primed to commence its journey of particle collisions. Now you might wonder, why the considerable depth? Well, besides shielding the collider from surface interference, the depth cleverly circumvents the rugged terrain of the Jura Mountains. This ingenious solution eliminated the need for extensive vertical excavation, resulting in significant cost savings. After all, who would opt for pricey surface land when there's ample room below ground? But what's the deal with this massive underground loop? Well, back in 2010, it made headlines by achieving its first ever particle collision at an astonishing energy level of 3.5 teraelectron volts per beam. To put that into perspective, it was nearly 4 times higher than the previous world record. And that was just the start. With a few upgrades since then, it now packs an even more impressive punch at 6.5 teraelectron volts. Picture this. 2 beams of particles zooming around, nearly reaching the speed of light before smashing into each other. That's the LHC in action. It's equipped with 4 specific collision points where these high-speed particles converge. And around these points, 7 detectors stand ready, eagerly awaiting the outcomes of these collisions. Typically, the LHC collides proton beams most of the time. But once a year, for an entire month, it switches gears to focus on heavy ions like lead. It's like the machine's special annual event. Now you might be wondering, why all the fuss? Well, it all boils down to our insatiable curiosity about the universe. Physicists are using the LHC to put some of the most mind-boggling theories of particle physics to the test. They're particularly interested in studying the elusive Higgs boson and delving into the potential existence of a vast family of particles predicted by supersymmetric theories. Ever wondered about hadrons? They're these tiny particles lurking within the subatomic realm, composed of even tinier constituents known as quarks. Think of them as the foundational blocks of protons and neutrons. The reason the LHC bears their name is because it's designed to smash them together, creating a myriad of byproducts. Many of these byproducts are incredibly short-lived and can't be studied through any other means. So, each collision within this expansive underground loop resembles a miniature version of the Big Bang. It offers scientists a fleeting glimpse into the very fabric of our universe, revealing its elemental components and the forces that bind them together. Built over the span of 5 years, from 1983 to 1988, this subterranean tunnel spans a whopping 3.8 meters in width and is fortified by layers of concrete. Above ground, there's a facility housing crucial equipment. Picture a room brimming with intricate control electronics, compressors, ventilation systems, and cooling apparatus. Now, here's where things get truly astonishing. The LHC churns out a staggering 15 petabytes of data annually. That's an immense volume of information to sift through. To manage this influx, an international collaboration engineered a specialized computing grid tailored specifically for the LHC's needs. This network stands as a marvel of modern technology in its own right. At the heart of the LHC's mission lies the quest to unravel the mysteries of a peculiar particle known as the Higgs boson. This elusive entity was like a spectral enigma, long theorized by scientists but never directly observed. Its elusiveness stemmed from its substantial mass. The LHC, armed with its formidable capabilities, aimed to produce multiple Higgs bosons every minute. It's akin to setting a trap for a rare creature, one whose existence many believed in but had yet to capture. And the LHC wasn't content with just that. In addition to its quest for the Higgs boson, it ventured into unexplored realms of physics, delving into the realms of supersymmetric particles and other hidden marvels of the cosmos. However, it wasn't all smooth sailing. Shortly after its launch in 2008, the LHC encountered a significant setback. A malfunction in one of its magnets resulted in damage to several components of the collider, halting its experiments for over a year. Yet, from 2009 to 2013, once it resumed operations, the LHC achieved remarkable breakthroughs, notably the long-awaited detection of the elusive Higgs boson. Following its initial success, the LHC underwent a period of upgrades, re-emerging in 2015 prepared for further exploration. Its second operational phase spanned from 2015 to 2018. Followed by a brief hiatus before its reboot in April 2022. Now, with an enhanced beam energy of 6.8 teraelectron volts, TeV, the machine's third phase promises to enthrall us until 2026. But something truly extraordinary occurred during its third phase on July 7th. Picture Earth's magnetic field as a protective shield enveloping our planet. On that fateful day, a mysterious rift appeared in this shield. This wasn't a momentary glitch either. It persisted for a staggering 14 hours. Imagine a window suddenly left ajar on a stormy night, allowing icy gusts to sweep in. This breach ushered in a torrent of solar winds, a phenomenon both baffling and awe-inspiring. Originating from the sun, these phenomena trigger massive geomagnetic storms, culminating in breathtaking displays of auroras dancing across the sky. If you're a fan of Stranger Things, you might recall the monstrous villain, Vecna. Some fans whimsically speculated whether Vecna had emerged through this very rift. While that remains a playful theory, the visual spectacle of the auroras was undeniable. But what led to the formation of this crack? The culprit is known as a co-rotating interaction region, CIR, emanating from the Sun. CIRs are expansive plasma structures formed when solar winds of varying speeds collide, akin to two rivers merging into a tumultuous waterfall. These CIRs, along with other phenomena such as coronal mass ejections, are hurled from the Sun towards Earth. When they make impact, we're treated to a celestial light show, the auroras. In the early hours of July 7th, a collision of such a CIR triggered a prolonged geomagnetic storm. The National Oceanic and Atmospheric Administration, NOAA, even noted that this storm was intensified by a preceding coronal mass ejection. Should we be concerned about these CIRs? Interestingly, experts offer a reassuring answer: no cause for alarm. Earth's magnetic field, our protective shield, routinely encounters such rifts. Normally, they swiftly seal shut. However, recent occurrences indicate that they can linger for hours. Picture residing in a house during a storm with a window that occasionally gets stuck open. While the majority of the storm is repelled, some water might seep in and dampen the couch. Similarly, while our magnetic shield deflects the majority of space storms, some energy manages to infiltrate. This can occasionally disrupt our satellites, radios, and power systems. In 2003, Harold Frey likened our magnetic shield to a drafty house. Most storms are kept at bay, but on occasion, some energy slips through the cracks. Sometimes just enough to create a spectacle in the sky or to interfere with our technology. Fortunately, there were no ensuing radio blackouts or power outages. Instead, this cosmic event gifted the residents of Canada and the US with a breathtaking surprise: the awe-inspiring Northern Lights. But wait, there's more. Scientists have unveiled a fascinating secret. The Sun is entering a phase of heightened activity, exceeding their expectations for this point in its cycle. What does this mean for us? Simply put, if you've ever dreamt of witnessing an aurora, your chances have just significantly improved. Over the next 3 years, anticipate the skies to burst with colours more frequently than ever before. Now, let's turn our attention to a monumental scientific marvel, the Large Hadron Collider, LHC. Think of the LHC as a colossal microscope, enabling scientists to peer into the smallest particles within our universe. Back in July 2017, it unveiled a host of incredible discoveries, including insights into the properties of the elusive Higgs boson. Fast forward to 2021, and the LHC had unveiled 59 new hadrons. Then, in July 2022, it caught sight of a new particle dubbed the pentar, composed of unique combinations of quarks. However, even the most remarkable devices, such as our beloved LHC, encounter challenges as time progresses. Their ability to yield groundbreaking results diminishes. But fear not, for scientists have a solution: upgrades. Currently, the LHC is undergoing a transformation known as the High Luminosity Large Hadron Collider. Commencing in June 2018, this initiative will empower the LHC to become even more adept at detecting rare cosmic phenomena. So, what's the LHC's claim to fame? In its initial run, it unearthed the Higgs boson. The LHC's subsequent phases delved even deeper into the mysteries surrounding this particle. Now, with its third phase scheduled to conclude in 2025, scientists at CERN are optimistic about doubling their data and potentially doubling their discoveries. Get ready for an exhilarating journey with the Large Hadron Collider, LHC, at CERN. Picture this. By 2029, this monumental machine, after meticulous preparations, will be ramping up particle collisions to rates 10 times more intense than ever before. But the excitement doesn't end there. This phase, anticipated to extend until 2042, will amass datasets that are a staggering 10 times larger than those gathered by the end of its third phase. Now, if you're curious about why this development is so significant, let's dive into the captivating realm of proton collisions. Imagine protons as bags brimming with colorful jelly beans. Within these bags reside smaller particles known as quarks, intricately bound together by even tinier entities called gluons. It's like witnessing a dance of nature's most minuscule components. Envision two of these bags colliding head-on, akin to two sets of jelly beans crashing into each other. While most collisions result in the jelly beans or particles scattering and reforming into familiar patterns, occasionally something truly magical occurs. Two quarks or gluons collide directly, compressing all their energy into an almost infinitesimal point before explosively releasing it. It's within these rare, high-energy moments that physicists have the chance to glimpse nature's deepest secrets. Yet, here lies the challenge. Within the LHC, bunches of protons collide an astounding 40 million times per second. To put this into perspective, envision attempting to capture a unique moment from a continuous fireworks display, where each collision yields a photo 20 times larger than those snapped on your smartphone. Collecting all this data would inundate a database with 1 million gigabytes every single second. That's an immense amount of data to process. The reality is, amidst the 40 million events occurring each second, the majority are ordinary. Amidst this deluge of data, there lies just one elusive Higgs boson event, waiting to be discovered. So, how do scientists prevent themselves from being overwhelmed by the deluge of data? Enter the trigger, a sophisticated computer system akin to a discerning photographer, meticulously selecting only the most intriguing few hundred collisions per second. These chosen moments are the ones that scientists will meticulously scrutinize later, in the hopes of unraveling the universe's mysteries. The Large Hadron Collider, LHC, acts as a colossal microscope, zooming in on the fundamental building blocks of our universe. Picture a vast machine striving to unlock the secrets of creation itself. Its primary objective? To discover previously unseen particles that could illuminate new cosmic truths. Some of these enigmatic particles might be exceptionally heavy, akin to heavyweight champions of the universe, disintegrating into clusters of smaller particles with immense energy displays. However, many scientists speculate that during the LHC's third operational phase, known as Run 3, we may not directly detect these heavyweight particles. Instead, we might stumble upon hints or clues, akin to finding a map rather than the treasure itself during a treasure hunt. These subtle indications could serve as teasers for more significant revelations in future phases. Now let's talk about a fascinating twist: dark matter. You've likely heard of it, this mysterious substance in our universe that's invisible yet constitutes a significant portion of it. Some of the newly discovered particles might have connections to dark matter, although they are exceedingly elusive, rarely manifesting themselves directly. It's akin to attempting to perceive the wind. You can't see it, but you can discern its effects, such as rustling leaves. Within the LHC, we search for other particles exhibiting peculiar behaviors, hinting at the presence of these invisible entities. However, there's a hurdle. These signals are often so faint that our detectors overlook them. It's akin to trying to catch a whisper amid the cacophony of a rock concert. Yet, with upgrades slated for Run 3, we're refining our ability to detect these subtle clues, akin to tuning our ears to pick up whispers in a crowded room. But hold on, there's an additional twist in the tale. Plans are in motion for an even grander and more audacious machine, the Future Circular Collider. Imagine it as the LHC's larger, more imposing sibling. This colossal particle smasher could come with a price tag ranging from 9 to 21 billion. However, not everyone is sold on this idea. Some argue that with such a hefty investment, we should explore alternative ambitious scientific endeavors. For instance, why not consider constructing a massive radio telescope on the hidden side of the moon, or deploying a space-based instrument to detect cosmic ripples known as gravitational waves? Renowned physicist Sabine Hossenfelder contends that this new gargantuan machine might not unveil the secrets we're eagerly anticipating. It's akin to investing in a state-of-the-art telescope that may not reveal any new celestial phenomena. Nevertheless, with the LHC poised for its third and even a fourth operational phase, the future holds plenty of promise. It's akin to being immersed in a cosmic detective story, uncovering clues one by one, with each stage promising further revelations. Think of them as episodes of an enthralling series, and we're on the brink of a binge-watching marathon. One recent surprise came in the form of an anomaly in Earth's magnetic field, which remained open for an unexpectedly prolonged period. It's akin to stumbling upon a hidden door in your home that you never knew existed. What other secrets await our discovery? However, according to thinkers like Max Laughlin, there might be cause for concern. Max Laughlin's theory proposes that experiments conducted at the European Organization for Nuclear Research, CERN, have caused humanity to transition into an alternate universe, giving rise to the phenomenon known as the Mandela effect. According to Laughlin, the high-energy particle collisions carried out at CERN might have inadvertently created a ripple in the fabric of space-time, leading us into a slightly altered version of our reality. The Mandela effect, coined after the widespread belief that Nelson Mandela died in prison during the 1980s instead of in 2013, describes a phenomenon where a significant number of people recall events or details differently from their actual occurrences. Advocates of this theory assert that such collective misremembering isn't merely memory lapses, but rather indications of our transition into an alternate reality. While Laughlin's theory presents an intriguing concept, it remains speculative and has encountered skepticism from many within the scientific community. The experiments conducted at CERN are undeniably groundbreaking, pushing the boundaries of our comprehension of the universe. However, there's no tangible evidence to support the notion that they possess the ability to propel us into a parallel dimension. Nevertheless, with such theories circulating, concerns about safety at CERN have surfaced among the public. Safety measures are deeply ingrained in every facet of its operations. Stringent protocols are established to minimize radiation exposure, with personnel working with particle accelerators and detectors equipped with dosimeters. Areas posing radiation hazards are strictly regulated. The facility employs robust engineering designs and shielding materials to contain radiation, while meticulous procedures govern the handling and disposal of hazardous substances. Electrical safety and fire prevention are paramount, with routine inspections ensuring compliance with international standards. Furthermore, CERN prioritizes the well-being of its staff. Comprehensive training programs and safety drills prepare personnel for emergencies such as fires, chemical spills, or radiation leaks. Additionally, an extensive medical service is available on site to address any health-related concerns promptly. Environmental safeguards are equally prioritized to mitigate any adverse impacts.